Dear colleagues, my name is Konstantin Morozov. Let me present you our work, improved GL model of behavior of complex multiprocessor system in failure flow. In modern world, automation is becoming more and more important. To ensure automatic and automated functioning of various systems and complexes, so-called control systems are used. The control system for so-called mission-critical systems, the failure of which can lead to significant material losses, should usually be very reliable and productive. For example, this applies to such systems as energy facilities, nuclear power plants, thermal power plants, hydroelectric power plants, transport systems like aircraft, trains, railway hubs, large industrial enterprises, space vehicles and systems, complex military equipment, and so on. Both these problems can be solved in case of building a control system based on the so-called fault-tolerant multiprocessor systems, FTMS. FTMS can continue a fault functioning in the event of failure of certain number or subset of its processors. However, the developer of FTMS faces the task of evaluating the reliability parameters of the developed system, in particular the probability of its trouble-free operation. This problem can be solved in different ways, which can be divided into two main categories. This first category includes approaches based on building certain analytical expressions for system reliability parameters. This allows to get their values with great accuracy. However, for complex and complex systems, it may be a very difficult task to build such expressions. It may be even necessary to develop a separate specialized method for each system. In other words, these approaches are usually non-universal. Approaches from the second category make it possible to evaluate the reliability parameters of the system with a given accuracy by performing statistical experiments with models of its behavior in the flow of failures. By applying the methods of mathematical statistics to the values obtained with help of such models on sets of random system state vectors, an estimate of its reliability parameters can be obtained with a certain accuracy. Accuracy can be increased, in particular, by increasing the number of experiments conducted and or by using specialized procedures for their formation. This category allows to obtain a universal method for any type of system. However, reliability accuracy may be limited, and it depends on number of experiments conducted. The model of systems behavior in the flow of failures takes as input the so-called system state vector and returns a certain value characterizing the state of the system as whole, which correspond to it. For example, 1 may mean that the system is operational, and 0 that the system has failed. The system state vector is a vector whose elements correspond to the state of each processor of the system. For example, 1 means processor is operational, and 0 that the processor has failed. On this slide, you can see the example. The operational processors are colored with green, and the failed processors are colored in orange. These are processor number 4 and number 6. You can see that corresponding elements of system state vector are equal to 1 or 0, depending on state of the processor. For failed processor, these values are equal to 0. The so-called GL model combine properties of graphs and Boolean functions. They can be used as behavior models of FTMS in the flow of failures, and such model is based on unidirectional graph. Each edge of each corresponds to a certain Boolean edge function that depends on all or on some of the elements of system state vector. If the h function takes a value equal to 0, then the corresponding h is removed from the graph. The connectivity of the graph corresponds to the state of the system, and if graph remains connected, the system is operational. If not, it fails. So you can see the example of GL model here. It's based on graph, and there are h functions, Boolean h functions, f1, f2, f3, and so on. A system that remains operational when any M of its n processors fail, and fails in case if a failure of a larger number of processors, and it's important that it may be any combination of them. It's just the number is important. So for this system, as well as the GL model corresponding to it, are called basic and are denoted as K of Mn. All other systems, as well as their models, are called non-basic. And unfortunately, real systems are not always basic. In particular, this may apply to so-called multi-module systems consisting of several subsystems. One can distinguish a special type of GL models, the so-called MLE models. It's named from minimum of lost edges because of one of its properties. It's this property that on vectors with n+1 zeros, the model K of Mn, MLE model, always lose a minimum sufficient number of edges. In other words, 2 edges. And this type of models have special properties. The first one property is that they are based on cyclic graph, and it simplifies evaluation of connectivity of the model's graph in particular. The second property is that about number of lost edges that we considered before. The next one property is that model of K of Mn have exactly a phi of Mn edges, where phi of Mn is n minus m+1. And the last one property is that on vectors with L zeros, this model will lose exactly psi of ml edges, where psi of ml is equal to 0 if L is less than m, or L minus m+1 if L is greater or equal to m. You can see the example here. This model is really based on cyclic graph. Some multimodal system can be organized in such manner that the processors of one subsystem, that can be so-called donor, can be used to perform some tasks of other ones, which are so-called recipients. Let's consider such multimodal system. Let the subsystem contain n processors and is resistant to failure of any m of them. So it corresponds to K of Mn basic system or basic model. So in other words, n minus m processors and n minus m capable processors are enough to perform tasks of the subsystem. So the rest of the processors can be used to perform tasks in of other subsystems. To build a GL model of the system, it will be useful to be able to obtain a vector containing exactly as many ones as the processors of the subsystem can be involved in solving external problems. It means problems of other subsystems. For the described subsystem, this number can be calculated using the following formula. We denote it as mu of ml, that is equal to 0 if L is greater or equal to m, or m minus L if L is less than m. Let's add one new model that is that contain edge functions that are dual with respect to the functions of the MLE model. So there is one model that is that has just dual functions. We will call such model a dual model, and using the De Morgan's rules, it's easily to show that the expression of the edge functions of the dual model can be obtained from expressions of the edge functions of the basic model by replacing conjunctions with disjunctions and disjunctions with conjunctions. So in a dual model that we can denote as K prime of Mn on the vectors of with L1s, it will have exactly psi of ml functions which are equal to 1. Here you can see examples of expressions of edge functions built for ordinary MLE model K of 3, 7, and for dual model K prime of 3, 7. As you can see, these expressions are really obtained from each other by replacing conjunctions with disjunctions and vice versa. Let's suppose that in K of Mn system, exactly L of processors have failed. So the number of workers on Kin processors is N minus L. We can see that in dual model K prime N minus M plus 1 N, exactly C of N minus M plus 1 N minus L edge functions will take a value equal to 1. Since N, M, and L are integer values, it's possible to show that C of N minus M plus 1 N minus L is equal to mu of ML. The vector consisting of the values of the edge functions of the dual model K prime N minus M plus 1 N will contain exactly mu of ML once. And this is exactly what we wanted to get earlier on the previous slides. We will call such model a redundancy model, and to simplify notation, denote it as R of Mn, and we will use this equation. In real system, it's possible that the possibilities of using excess resources of one subsystem to restore the opportunity, the operability of another may be limited. For example, it may be possible that number of processors that may be transferred from one system to other is limited by some number. So we may need to reflect this in model. From a vector of length n containing L1s, we need to obtain a vector of length h, where h is less than n, containing exactly k that's equal to minimum between L and h ones. The model of k of n minus h plus 1 n has exactly h edges, and on vector with L1s will lose exactly c of n minus h plus 1 n minus L edges, and exactly we will denote this as rho of L that is equal to h minus c of n minus h plus 1 n minus L h functions will take a value equal to 1. We can show that rho of L is equal to h if L is greater than h minus 1, or L if L is less or equal to h minus 1. And take into account that L and h are integer values, we can see that rho of L is exactly minimum between L and h. So that's also that we wanted to obtain. Let's call such model a constraint model and denote this as L of hn. And we will use also this type of expression. So let's formulate recommendations for building models of systems like donor and recipient. The model that represents the behavior of donor subsystem is an ordinary basic MLE model that is built with appropriate parameters of the subsystem, number of processors, and fault tolerance rate. So it's just a basic MLE model. And the elements of the system state vector corresponding to the processors of the donor subsystem are used as input for this model. In addition, there may be built a dual redundancy model representing transfer of available redundant resources processors. The input for this model is the same as for previous model, so it's that part of system state vector. If it is necessary to limit the number of processors that can be transferred, an appropriate constraint model can be applied to the vector constructed from the values of the H functions of the redundancy model. And the model of recipient subsystem is also an ordinary basic MLE model. However, as input, it uses the elements of the system vector corresponding to the processors of this subsystem that are combined with the values of the H functions of the corresponding redundancy or constraint model. Thus, both model parameters might be increased in T on value T, where T is the number of these H functions. So let's move to examples. Here we can see the basic example. So there is a system that consists of two subsystems. The first subsystem contains 10 processors and is tolerant to failure of no more than 5 of them. And the second subsystem contains 7 processors and is tolerant to failure of no more than 3 of them. And redundant processors of the first subsystem can be used to restore the performance of the second one. So it's denoted with this arrow. So we will use redundancy model R510 that is a dual model K prime 610 as it was shown on previous equations. So we will use this part of system state vector that corresponds to first subsystem to build its model. This model is just ordinary basic MLE model. And also we will use this part of vector to build this redundancy model that is dual model K prime. And we will use the second part of vectors that correspond to the second subsystem and combine it with values of H functions of redundancy model to form the input vector for MLE model of the second subsystem. And because of redundancy subsystem, the redundancy model has 5 H functions, we need to increase both parameters of our model compared to parameter of subsystem on value equal to 5. So it means that instead of K37, we use K812. The second, in the second example, the second subsystem can also use its excess resources to restore the performance of the first subsystem. So we have the bidirectional error now. And we use, in this case, we use also one more redundancy model. It's R37. That is equal to dual model K prime 57. So it's here. And to build model of first subsystem, we combine the original input part of input state vector with H values of H functions of this second redundancy model. And we need to, since there are 3 H functions of this redundancy model, we need to increase both parameters of the model on value 3. So instead of K510, we use K813. And in third example, it is equal to first example, but the number of redundant processors that can be transferred is limited by value that equal to 3. It's here in this arrow is shown that the number is limited, not greater than 3. And in this case, we need to use a constraint model L35 that is equal to MLE model K35, and we use it. We apply it onto values of H functions of redundancy model, and we obtain 3 values that we combine with with part of system state vector corresponds to second subsystem, and we obtained this model. We need to increase both parameters of the second subsystem on value equal to 3 because of 3 H functions. So instead of K37, we use K610. And it's here we obtain the model of models of these subsystems. So let's move to conclusion. The work is devoted to the problem of building GL models of complex multimodal systems, in which it's possible to transfer some of the tasks of one subsystem to another one in order to restore operational efficiency. This proposed the so-called dual model, the H functions of which are formed from the H functions of the original GL model by replacing conjunction operations with disjunction operations and vice versa. Dual model can be used as so-called redundancy model to indicate the number of processors that can be used to restore the performance of other subsystems. It's proposed to use so-called constraint model for cases if the number of such redundant processors should be additionally limited. And system of the donor recipient type, as well as the variations in which one of the subsystem, the so-called donor, can use its processor to restore the performance of another that is called recipient, are considered. For each case, methods of building a systems model based on combination of dual and ordinary GR models are proposed. And finally, the application of the proposed approaches for models of some of the considered types is shown using specific examples based on experiments which were carried out by the authors. Thank you for your attention.